Today we start our second module. Name of its model is dynamic programming. And today we will start with the several tasks of dynamic programming. Unfortunately, I have no presentation today, but I think that we can save this board after the lecture and send it to the students. Yeah, do we have this?
Yeah.
Yeah, nice. So about dynamic programming and common theory about it. Yeah, today we talk about dynamic programming part 1. And so this lecture and next lecture consist of many different tasks in which we find in the solution of which we find methods equal to names as dynamic programming. So I think there is no it's one way to understand dynamic programming as the set of methods that can you use when you solve some problems. So, firstly, about common theory under this topic. About some reasons why you can use dynamic programming and don't use any other algorithms. Firstly, you can find different tasks. Yeah. You have tasks. In each you find two main parts that show you that you need to use these methods. Firstly, you can split your tasks for some subtasks. And it's the first step. It's the first main part of the dynamic programming. And the second important step that you can solve these subtasks independently. And we find these two steps in next examples that we talk about today. but you can see that it's very common language that we can talk about the problem. And of course, dynamic programming is equal to different recursive algorithms. But as we see in different tasks, we find ways that we can use dynamic programming is more comfortable than the recursive analogous. So it's about steps or main part that we need to find in the tasks to use dynamic programming. And then, for example, how we use what is the difference between dynamic programming and recursive algorithms? For example, you know what is Fibonacci numbers? Yeah. You know that f0 equal to 0, f with the index 1 equal to 1. And we have recurrence formula for them. Yeah. So, for example, we need to find, for example, f with the index 5. Yeah. How we can find it? Recursive, for example. Yeah. We can use this formula and say that to find f5, we can find f3 and we find f4. Yeah. Then we can say that we don't know f with the index 3, and we can repeat these recursive algorithms. Yeah. We say that it equal to f1 plus f2. Yeah. f1 we know, f2 we don't know, and we repeat it. And we repeat this algorithm for this part of this tree. Yeah, and we see that, for example, for f with index 5, what is the number of subtasks that we need to solve? Yeah. For example, you can say that node is equal to one subtask. Yeah. For example, we need to find f with index 3, and then number of the nodes has exponential or asymptotic. Yeah, you see. So, yeah, native recursive algorithms has asymptotic time equal to 2 power n. You know it from the other courses, yeah? You know this asymptotics from the other courses. Yeah. So how we can solve these tasks to find Fibonacci numbers in the way to spend less than exponential time for it? You don't? Or do you know? What is the time? Or guys in the Zoom can say? Yeah, to avoid exponential growth of the subtasks, number of subtasks. We can find, yeah, of course. Interesting, yeah. Ways to prevent large spans, time spans. First, we can use analytic formula for Fibonacci numbers. Have you ever seen the analytic formula for Fibonacci numbers? Yes? It's equal that Fn equal to C1, 1 in, yeah. Yeah, you see it, yeah. With some coefficients and lambdas. Okay, but for example, if we change this recurrent formula, we need to get paper, find analytic formula, and of course to find these two number, lambda 1 and lambda 2, we need to solve some polynomial equation. And of course, in the general way, we need to use some approximation algorithms to it, and this way has its own reasons to not use it. Because of analytic formula, we have no analytic formula for difference recurrence if it isn't a linear recurrence. So, for example, if I add this power 2, yeah, you cannot use common way to solve the linear recurrence equations. So, of course, this way we can use to solve this task for Fibonacci numbers, but in the common way, this way will be too complicated as the native way. So, second way that we can use to solve this task, we can say that we have very similar subtasks. We can say, for example, yeah, that here we have two subtasks to find F2, F3, and it's... Yeah, and then we can use it, yeah, of course. So, of course, we can say that we can find in this tree similar subtasks, yeah, to find, for example, Fibonacci number with index 3. And then if we one time solve this task, we can store this information and use when we find it in the tree again. So second way to we can use dynamic programming in this task is that we can say that we can store the results of subtasks. And then if we find a similar subtask, we won't spend time for complete it. We see in the memory, yeah, and find the result of this task, of this subtask. And this way to store the results of subtasks names as memorization. Because we can use memory to spend to decrease number of subtasks that we need to solve in the solution of our common task. Okay.
Memorization. Where should we stop memorizing?
When we start our algorithm, we get, for example, this number. It's equal to. We said that it is equal to n, and then we finish when we find this result of this task. And of course, in the different tasks, I write now here. In the difference tasks, we can use different structures for memorization. And our dynamic algorithm ends when we find the results of our task. It's understandable. Yeah. When we find the results of initial task. So in this example, yeah, annoying.
You wrote erase it 2 times.
Oh, thank you. Okay. In this task, task of Fibonacci numbers, we can say that if we need to find Fn, we can find F0, F1, F2, F3, etc. and store these numbers. So when we need to find Fn, f with index n, we can pop number f with index n minus 1, repeat it for f with index n minus 2, and find the sum of these two numbers. So if we see this algorithm, when we find initial number of Fibonacci numbers, then we repeat to find f with index n, we repeat our algorithm, we repeat this formula and find the new number by it. So, as we see that time complexity of the solution is equal to, you know, what is the time complexity? Linear, yeah. It is equal to O from number of Fibonacci number, index of Fibonacci number that we need to find.
In the negative equation, it will be log n,
right? No. Here we have exponential time space complexity. So, yeah, 2 power n. It is time complexity. And due to this time, we want to find other way to solve this task, because exponential time is very big in a lot of cases. So, but what is we can say that, okay, native algorithm is worse than this dynamic algorithm due to time complexity. But in which way native algorithm will be better than the dynamic algorithm? Do you know?
Memory?
Memory. Yeah, because of memory. And of course, we say that to solve this task with dynamic algorithm, we need to use memorization. We need to store previous Fibonacci numbers. And of course, if we use, for example, array for Fibonacci numbers, we say that space complexity O from n, because we need to store previous numbers. And of course, we can say that due to this formula, we can store only previous two numbers and change it in each step. And then we change this asymptotic complexity to O from 1. And of course it will be better, but it works only due to this very simple task. And in the other task, we cannot upgrade it with decreased number of storing numbers. So when we use dynamic algorithm, if we use dynamic algorithm to solve some tasks, we need to understand that we change the increase the lower time complexity to bigger space complexity. Yeah, we change. So we need to understand, is it better to store bigger data and get the speed up in the time complexity, or use other algorithm and have no problems with the memorization? Because, for example, in this task, we need to store only integer number, and memory that we use for it very small, and a lot of language properties or properties of hard memory become more quicker solution of this storing, because of a lot of using of integer numbers. But for example, if one result of the subtask is equal to, for example, a big text, for example, or some structure. So if we store linear, for example, if we store n such structures, we can spend a lot of time to make it, to connect it between each other. So you can understand when we use such algorithm, we need to understand how much we spend to memorization, of course. How much we spend to memorization. And it is common theory, and then we need to spend our time to different tasks to understand why dynamic programming is better than other algorithms, and we see it with the other tasks. I see now first I want to talk about longest increasing subsequence.
Sorry,
Yeah.
but I didn't understand why we need big O of n for memorization in the Fibonacci example.
Can you repeat what we?
I didn't understand why we needed space complexity of big O of n to in the dynamic way.
Why why we spend O of n space complexity for
Yes,
this realization? Because if we store Fibonacci numbers from 0 to fn, we spend we need to store n numbers, and we get O at n, O from n space
but
complexity. Yeah.
but we don't need the n Fibonacci numbers.
Yes, that's why you can be.
Yeah, so I write that in this task we can
Okay.
improve it to O from 1, of course. But in some tasks we need to store O from n, not in this task, but in the most tasks that we use dynamic algorithm, we cannot improve this space complexity. And we see in the next task that we can store a lot of data to get less number of subtasks that we need to solve. So we, I write here that we change time complexity, yeah, to space complexity. And of course, here we can improve this algorithm such that we cannot spend anything, and we cannot spend a lot of space and get the speed up in time from exponential to linear. But in the next task, we see that we can improve the time complexity and get the speed up. But in this way, we spend bigger space to store some data. So in this task, you are right that we can not to store all of these Fibonacci numbers and store only pair of these two Fibonacci numbers. Yeah, we firstly store these two Fibonacci numbers, then we change it with this pair, etc. And finally we get pair of these two Fibonacci numbers. And you're right that if we change array to this pair of integers, we spend only O from one space to it. But it's due to this simple task, because of Fibonacci numbers, it's I think training tasks for this topic. But now we face with other tasks and see that of course we cannot increase we cannot decrease space complexity. Yeah. Do you understand?
Yes, thank you.
So, about the second task, about longest increasing subsequence, it's interesting that in the there are two tasks that I want to talk about. Firstly, imagine that we have a sequence of integers. Here we have a with index 1, a with index 2, etc., a with index n. And input data, it's n and this sequence. And we need to find subsequence A with index n1, A with index n2, etc. A with index nk, such that, of course, it is the subsequence of the of this sequence, and it is equal that n1 minus n2, etc. Here is due to definition of subsequence.
N1 or A N1?
Hmm?
N1 or A N1?
N1, N2, and we say that the indices of this A will be increasing sequence, and of course it is first. And the second that A n1 yeah due to increasing sequence. So now we can find this. What is the native algorithm for it? For there are different ways to improve the algorithm. Firstly, I can say that it is two exponential algorithm that we can check all the subsequences of this sequence. Yeah. You can check all subsequences is it increasing or not? So, what is the time complexity of this solution? How many subsequences in this sequence?
N to the power n?
2 power n, yeah.
To the power n.
2 power n. Because any this number can be in subsequence or not in this subsequence. And then we find production of this variance. So, and space complexity? So, all from 1. Because, for example, we can set iterator from 0 to 2 power n minus 1. And then we find this sequence by this number, and don't spend any other space. Or we can store, yeah, we need to store this sequence, so we need to use, so we need, it's equal to n because of storing this sequence, of course.
I didn't understand why we need 2 to the power n time complexity. Can you please explain me?
Time complexity, why it is equal to, okay. Can you ask yourself how many subsequences or subsets, in the set 1 to n? Are. How many subsets are in this set from 1 to n? 2 power n. And for each subsequence, we can say that this subsequence we can code with this sequence of integers n1, n2, and k, and it is the subset of set of from 1 to n. So time complexity is equal to 2 in power n due to a number of subsequences of this sequence. For example, if n equal 2, and we have sequence A1 and 2, we need to check sequences A1, A2, A1, A2, and empty sequence. So number of these subsequences is equal to 2 power n 4. Do you understand?
Yes, thank you so much.
Okay. So, of course, it is native algorithm, and of course we can improve it because we understand that, for example, if subsequence is increasing, so any subsequences is too increasing, and we need to find, for example, subsequences that ends in place that we choose, for example. So the second way that we can improve first algorithm, we can say that for each a with index k, we can find the longest increasing subsequence that ends with AK. So, how we can find this subsequence? Interesting that if we use different structures to store previous longest increased subsequences, we get different time complexities in the algorithm. Firstly, we can say that we can store the length of the longest increasing subsequences for all numbers from A1 to A with index k minus 1. We can store it for the previous numbers. So if we know that what is the length of the longest increasing subsequence that ends in a k minus 1, a k minus 2, a k minus 3, etc. a1. We say that we can check if am minor than ak. We think that the numbers are different. So if there can be equal, I say that it can be less or equal to right part of this inequality. And if now I write some pseudocode of it, yeah. If you find am less than ak, for these numbers, we can compare their lengths
K and M. Which one is bigger?
m minor than k. And if we find am such that it is less or equal than ak, we can say we know for this number that the biggest subsequence that ends in am has length Lm, for example. So we can add to this subsequence ak because of this inequality and increase this subsequence. Yeah, so I can erase this if.
So here, K is equal to M plus 1.
Hmm?
K is equal to M plus
1. No, it can be bigger than m, but not equal to m minus plus 1. And so for such am that AM less than AK, we find the biggest number LM. And for example, the biggest number LM is equal to alpha, and we said that LK is equal to alpha plus 1, because we find the longest subsequence that end in AM, and length of this subsequence equal to LM, and we add AK to it. So the length of this subsequence equal to L with index m plus 1. I can write this algorithm steps by step. Yeah. So algorithm. Firstly, make empty array L n and set each Ln equal to 1. Because of course we know that the subsequence can be can consist only from one number, and it can be equal to and then this subsequence has the length equal to 1. Then we set, for example, we set iterator to for it we go from 1 to it minus 1 and compare AM and AK, yeah? We change M from 1 to it minus 1. And if AM less than AK, we say, okay, then we can find the longer subsequence. And how we can find? We say that L from iterator will be maximum of the length that we have already found and the length of this subsequence, this subsequence that we now find in this step. So what is the length of this subsequence? It's equal to L from M plus 1. And we increase it and repeat second step while it's less than n. So when we get this array and we find all increasing subsequences that we find the longest subsequences, increasing subsequences that end in with the number a n. Then we say that the longest increasing subsequences in all sequence will be the maximum of this array. So the answer is maximum of this array. Do you need to make example of working of this algorithm? Guys, in the
I think yes.
Yes, okay. So example, if n equal to 8 and we have, for example, this, for example, it's equal to a1, a2, a3, etc. And then it says that L initially L equal to 1, 1, 1. Here's the first step. And it's equal to then we repeat second step. We say for a2 we find a1 minor than a2. So L of 2 is equal to maximum of L1, L2, L1 plus 1. So it's equal to 1, it's equal to 2, and so it's equal to, yeah. And then we end of this step because we got this number. And then we set iterate equal to 3 and go to step 2. Yeah, I write these numbers over the numbers in this sequence. Yeah, the longest increasing subsequence that ends with the first number equal to 1. Here 2. Here we compare A3 and previous A and say that there are no numbers such that they are less than A3. So it's equal to 1. Yeah. So no AM such that M higher than A3. So we repeat, yeah, we set iterator equal to 4, go to second step, and then
I think it's understandable now.
Oh, it's
I don't
understandable.
have, yeah,
Nice.
thank yes.
Yeah. So what is the L from 4? 4. Yeah. It's equal to 3. Because we can find this subsequence. We find that A with index 4 bigger than the previous numbers, and then we find the maximum of these 3 numbers and get plus 1 for it, and get the length of the longest increasing subsequence that end with the 4th number. For this number, 4. For this number, no. 21 is less
It's
than.
smaller.
Yeah, it's 4 too. For this number,
Also 4?
no. Because 4 is less than 8. No, not 2. It's equal to 3. Because 4 is bigger than this number, and this number. And we compare these 3 numbers and find the maximum, it's 2. And the length of the increasing subsequence that end with this number will be 2 plus 1. Why? For this number, it's equal to 1. Yeah.
Yes.
So after that, yeah, we say that the maximum of this number is equal to 4. So 4 answer. And of course, we can find if, for example, we store the link for the previous number, not only the number, we find that this number can connect with 8, it connect with 3, we connect with 2, and then we find this subsequence. So, of course, if we need to find not only the number of the numbers in the longest increasing subsequence, we can store links and then find such subsequence with these links. So, okay. Of course, we need to understand what is the space complexity. And time complexity of this algorithm. Linear, yeah. How many times? Oh, yeah, n square. Yeah, because for the second number we repeat comparison one time, for the third two times, etc., and we get the sum of 1, 2, 3, etc., n minus 1. So it's equal asymptotically to n square. So, of course, it's better than 2 power n. But we can solve this task with time O n log n. So, do we need now break time, or we talk about the third algorithm for solve this task, and then we get break time?
Do the dynamic way and then go to break.
Okay. So about the yeah, about this increasing. Now, what do we store now in the third algorithm, or in the second algorithm? We thought the length of the increasing of the longest increases of sequence such that the end number is equal to a with index k. But we can use in this way different array that we store and upgrade each step. We can change n to, for example, I name it as fix array. And when iterator will be equal to k, fix from e, I think when it will be equal to k, fix from E will be equal to number am such that there are there exists the increasing subsequence with the length e. And such that there exists the increasing subsequence with the length e, and ends is am. And it is the minimum of such numbers. So you can try to understand how we will use this array to get this time complexity. And now we get break time. We continue with this third algorithm to solve this task to find the increasing or the longest increasing subsequence with the spanned only or from n log n time. And I say that we need to use this array. It's the difference between previous algorithm and new algorithm. And we say that this array, we say initially that this array has very important property. Do you know what is this property of this array? Can you see to this definition and say what we can say about these two numbers?
Fix I is bigger than fix I minus 1?
Yes. And so we can say that there is invariant that fix is sorted array. by increasing number. So it is interesting that it is sorted. So when we try to find subsequence that was interested for us, we spent n time to go through. Yeah, we remember that it's equal to n power n, or multiply n, and we spent this time to find the longest subsequence. To find interested for us index of m. Interested for us index I think. And now if we work with sorted array, we can find it. Yeah. We can change it with log from n number, because we can use what we can use to find a number in the sorted array.
I can start from I.
For example, if we need, if we have array that has length equal to n, and it is sorted, and we need to find a number in this array. No, not the biggest. Some number. Binary search, yeah. Binary search. And now we understand why this picture not so complicated, and why we can use it to solve this task. For example, firstly, we work with this example, and I can maybe repeat this example 2, 3, 1. And then 8, 1, 2, 3. No, not 33. Okay.
21 or something?
Oh,
Yes.
-1, yeah. Thank you. And initially, we said the this array to -1. -1, -1, -1. Yeah. Then we see on this number, you see that there is no any increasing subsequence, and set, that is the first increasing subsequence that we find. Yeah, but no. We need to set these numbers equal to plus infinity. Etc. Yep. Then we see this number. It's equal to 3. And we find in this array place where we need to input 3. Because it is sorted array, and we find place by binary search. We spend log from number of log from n time to it, and we find that we need to insert here. So we change plus infinity to 3. And other numbers don't change. Then we see at this number. And we say, okay, we have this array and we need to find place where we need to input this one. And we find here. But we have no number with -1. Yeah, with the iterator equal to -1. So we change to with it. So here we write 1. Then we see at 8, find the place where we need to input. We find here, yeah. And so we change it to 8. Do you understand in which way? No. In each step, we find the place to insert new number. Using binary search. Etc. Yeah. We can think set it. No. So, let's try to understand what will be in the array after the next step? Here, what is the next?
1, 3, 8, 53.
8, 8, 4, 3. Nice. Okay, next step.
We add 21
Where?
after 53. No,
No.
no.
We change 8 to 21.
53. 21, sorry, yes.
Okay, next step.
Instead of 3, we put 4.
We change, no. We need to change not, no, yeah. You're right that we need to change 33 with 21 because the longest subsequence with that ended with 21, 2, 3, 4, 21. So yeah, we need to change. When we find the place, we change the right number with it.
So now we change 8 to 4.
Yeah, we change 8 to 4.
And then minus 2, 1 to minus 2.
1 minus 2, yeah. And then we say, okay, the number that is not equal to plus infinity is 21. It is the bigger number in this array that is not equal to plus infinity. So it is in the fourth place in this array. So the answer equal 4. Yeah. So it is in the common way it works similar. Yeah. Each step we find in this array place where we need to insert new number, and to find it we spend log from n time, and we repeat it for all the numbers, and so we spend only n log n time. Do you understand how it works?
I think yes.
Okay.
And here the memory will be n square. The memory.
Time complexity and space complexity, or what?
Yes, space complexity.
Space complexity? No, it's equal to O from n because we spend only O from n to this array. But as you see, uh, time complexity. And here we get a space complexity equal to O from n because of store of our sequence. And of course, difference between this algorithm and the previous, that in the previous we store iterators, yeah? We store indices of, we store lengths, yeah? What is the difference between third and second algorithm? Firstly, we see that third is quicker. So it is the improvements of the third algorithm that we got better asymptotical time to it. But in the second algorithm, we store lengths. And of course, it is integers. Always. It is integer. And in third algorithm, what we store? Not numbers. We store elements of the sequences.
Yes, that's right.
Elements. So, if you realize third algorithm in a way when we copy elements from the sequence in the fixed array, then if elements, yeah, we don't know what it is in common way. Yeah, in this example, of course, we find the solution of the task in which we talk about sequences of the integers. Yeah, and so we say that elements of the sequence equal to integers, and first array with name n was contained with integers, and this array fix also is contained with integers. But you can use these algorithms to find the longest increasing subsequence where sequence can be complicated with not integers. And in this way, you need to understand that when you copy elements from the initial sequence that you get in the array fix, you can spend additional time for it, and it can be very difficult for understand time complexity, because these structures that you can use for the elements can be very very large, and so when you copy it, you spend more time than, for example, all this time for all the algorithm. Do you understand what is the I think it is advantageous, the second algorithm that is disadvantage of third algorithm. But of course, I think we try to add it to the homework, but you can think about it. How we can improve it. Not to copy elements.
In the second.
In the third algorithm. In the third algorithm. Because now we say, or you see, we leave this definition. Question? Hashing? Maybe you can use hashing. You think about it in the home. At home, I think. And of course, you need to understand that initially this array full of numbers, am, and you need to change it to get speed up. Understandable? Guys in the Zoom, do you understand what is the difference in this way between in the end that by the definition fixed array contains elements of sequence, and you can improve it to change this array with different codes, for example, that you can use to hash your elements and not copy it. For example, of course, it's not only one solution to it. Guys in the Zoom translation, do you understand last discussion?
Yes.
Do you understand why we need to understand what is the elements of the sequence and why time complexity depends on it?
Time complexity depends on the elements?
Yeah, because if you use definition as on the board, you copy elements and you can spend a lot of time to it.
Sorry, we are talking about space complexity or time complexity?
Time complexity.
Ah,
Because when you copy elements, you spend time on it.
yes.
And if structure that you use for elements is very big, you spend a lot of time to copy it, and there is no interesting that you spend for the steps of the algorithm if you spend a lot of time to copy it.
Yes, understandable.
So it's all about the longest increasing subsequence, and Oh yeah. Third. No. Third task that we talk about today. It's dynamic programming with the graphs. And I think graphs that we want to talk about today, it's trees. And there are different tasks that connected with dynamic programming and trees. And 3.1, for example, each vertex in the tree has its own number. Has its own number. As in the weighted graph. Yeah, do you remember it? Weighted graph. But vertices, but now vertices are weighted, not edges.
So the vertex has the same index as its own weight.
Yeah.
Huh.
As an example, I can write here. For example, this tree.
So we can have two times.
Hmm?
We can have the same number two times.
Yeah, for example, 3 is 3. And task is that you need to find the path with the maximum sum.
And we have to visit all of the vertices, or we can skip some of them?
Please repeat. What do you?
Can you hear me well?
Now, yeah, I hear you. Well,
Okay. We have to visit all of the vertices, or we can skip some of them.
if we find, for example, this way, we need to sum all of the vertices in this way, in this path. And we cannot skip, for example, this vertex. We cannot do it. We sum all of the vertices in this path. Hmm? Oh. No. We can find, for example, this rows too. And of course, as we start earlier, what is the native solution?
BFS?
No, no. It's not the first. How many paths are in this graph?
How many?
How many paths are in the graph? We know that in the tree, between two vertices, there is only one way. And so, how many paths in this graph?
N to the power 2 minus 1? No. It's for something else.
N minus 1 divided by 2. Because we can choose two distinct vertices, and we know that we find only one way between these two vertices. This one and this one, for example. So, why it is n? We can choose any vertex. Then we choose any other vertex. And then we say that we have no direction in the path. So we divided it by 2.
Sorry, once again, I didn't understand.
Do you
The
understand?
reason that it's n times n minus 1 over 2. The reason of that formula. I didn't understand why the number of paths is n times n minus 1 over 2.
Okay, I can repeat. Firstly, what is the number of vertices?
N.
N.
Here in this example. Okay. Yes, no n.
Arguments? See that if we want to find path in the tree, we need to find two ends of this path. First end we can find by choose any vertex. Then we can choose any vertex, but not the first one. And then we say that we divide it by 2 because there is no direction of the path. But of course, if you in other courses you say that we have direction of the path or what? No? Yeah. No? Okay. So you can see that this is equal to and choose 2. Do you faced with, or did you face with this number?
Yes.
In the commentaries. And of course, you can see at this formula as you choose two vertex, and there is only one path that connects these 2 points. So, to native solution is to find all the paths and find the sum of these paths and compare it. Yeah. So how many time we spend on it? Time complexity.
Time complexity.
Yeah.
The number of
It is complexity. complexity
O of n squared.
O from n, what is here? Why you say n square? Because of number paths, yeah? But you can see that every path, a lot of paths can be equal to n by their length. Yeah, when we find the sum of the weights of the vertices in the path, we spend nearly n time for it, and we repeat it this time n or n cube. Yeah. In the worst case, we spend n power 3, because n power 2 it is asymptotical number of paths, and for several paths we spend nearly n time to find its sum of weights. So it is time complexity of this algorithm, and it's very big, because n can be billion, for example, and billion in third power, very big. So,
Professor,
of course,
I didn't understand time complexity. Why n cube?
Because after we find all the paths, we need to find its sum.
Why do we need to find the sum?
Because we compare summary of weights of paths and find the maximum.
Okay.
We compare not the length of the paths, we compare the summary of the weights in it.
Yes.
Because
Okay.
if we compare lengths of the paths, of course we need to find diameter, and you solved this task in the previous contests. But now we have weights in the vertices, and we need to use other algorithm. So we need to find sum, and we spend on it nearly n time. So it's native algorithm, and of course it's the worst case to it to solve it. And what is the dynamic algorithm? Dynamic solution. For example, we can see at the abstract tree without weights.
Scheme on weight between two subtrees.
Yeah, we can say that we can divide tree in two and solve this task for them. It's interesting, but we need to remember that there are different ways to find maximal path in the graph. Firstly, we can find maximal weight in a subtree, for example. Maximum path. In the subtree. Then we can find maximum path as the path that ends in the root. And of course, there is finally the most complicated case. What is the most complicated case? When we find the maximal path, not in this subtree, not as the path that connects vertex in the subtree with the root, but the path that connected different subtrees. It can be, for example, such path. Yeah. It is the third way. The maximum can connect vertices in the different subtrees. And so we need to store a lot of information to understand what is the maximum paths of each type. And then we got the answer at the maximum of 3 passes, that is maximum of these types. Solution. We solve the task for subtrees. And find the maximum path of each time. These steps. Yeah. 1, 2, 3. And then we find the maximum paths for the roots of these three types, and then compare them and find the longest. So about algorithm. Firstly, we make two arrays. First array is the maximum path in the subtree, and second array, it is the maximum path that end in the root of this subtree. So one we say as answer, because for all three we get the answer. It is the maximum in the subtree. And second array contains paths that ends in the roots. We name it as RP, root paths at the maximum of the paths in the subtree that starts in the roots. And of course, initially we have weights of vertices. So we understand how to divide our big task for subtasks to find results of the subtrees, and then find new answer with these arrays. So how we realize this algorithm? For example, we have roots of our tree, and we have subtree 1 and subtree 2. And I name adjacent vertices as U and T, for example. That is, they are adjacent to roots of the tree. So, very recursively, find the values of the subtrees S1 and S2. Then, okay, if we have these three arrays, what we can say about the, for example, RP for the R? What is the maximum path that starts in the root? For example, we can say it can be path from one vertex, R. So it's maximal of only weight of R. Then we say, okay, but it can be path that contains more than 0 edges. Yeah, for example, 1 edge, and other vertices must be in S1 or S2. And so, if we find no, it starts in the root. So we say that, for example, if this root will be in this subtree, yeah, we say that the sum of this path will be equal to weight of the roots and RP of U. Do you understand? Yeah, it's roots. Yeah, and RP of T plus weight of root. So, due to other way to find this maximum path, yeah. So it's new RP for the roots. Okay, and the maximum of the paths in the subtree. How to find it? I need to find maybe we can copy this picture. No. If we clone it and nope. Unfortunately, okay. I write new tree. For example, yeah. and to understand what is the answer of roots. What is the maximum path? Firstly, we can say that the maximum path may be only path consists only one vertex, yeah, as in the RP. But as we understand that there are a lot of paths that ends in R, and we know the maximum of it. It is RP of R. So we can write here RP of R, not weight of R. Yeah, because it is the maximum of the paths that starts in the root. So, for example, it can be such path. Yep. Okay, and we know that maybe the maximal path in the graph equal to path that connects two vertices in different subtrees. Yeah, and how we need to find it? We can say that if it's U, yeah, it's T, weight of this path equal to, do you understand what is the weight of this path? It's equal to T, not plus but it's not true, because we find these two, or if we find maximum of these two numbers, we find the maximum of the paths that contain root. But maybe the maximum paths, the maximum path doesn't contain the root. And in this way, this path must be in one of the subtrees. So after comma, but I can find, for example, maximum path as the maximum path in one of the subtrees. And in this way, we need to compare this maximum with maximum for each of the subtrees. And this maximum is equal to answer of U, answer of T. That's all. So it is the formulas of the RP and ANS. This way, in this way, we change these two trees, and then we find the maximum of the tree. And what is the answer of the algorithm? If you understand previous steps, you can say that answer for the task. What is the answer for the task? We can see here that answer tree of ants, it is the maximum of the passes in the subtree. And to find the maximum in the tree, we need to get ants of what vertex? Guys in the Zoom, maybe you know. I can add that ants from vertex V. It's the maximum of the passes in the subtree with the roots V. And in which tree we need to find maximum of the passes? With what row? With what roots? With what roots? With root R. Yeah? And answer for the task, it's answer.
The one here, yes.
Yeah, but it's recursive formula for the subtrees cos2. Yeah, when you go to the subtree, for example, S2, yeah, you can say that answer of T is equal to RP of T, etc. And here, yeah, you're right that. Yeah, it is the roots of the tree. As we see in each step, when we go down in this tree recursively, we spend only constant time to arithmetic operations and comparison. So we say that space and time complexity for it is equal to O from n and O from n2. And about space complexity, of course, we spent linear time, linear space to store n's and rp, but you need to understand that we need to store 3 trees now. Yeah, because this tree in our algorithm become tree with the complicated nodes. Each node have V, RP and ans number. So of course, asymptotically it's equal to O from n, but if we want to understand what is the coefficient before it, it will be bigger than in the native algorithm. But of course, time complexity is better than in the native algorithm. Guys in the Zoom, do you understand how we compute these numbers recursively, ans and rp, and why these two numbers, these two arrays, connect with the with our task. Masoud, Stefan.
Yes, it's okay.
I think, can we repeat the task again? Like, what the goal of the task? What is the thing that we are trying to reach?
Try to reach what?
Yeah, the goal of the task. What is the goal of the task?
The goal of the task? Find the path with the maximum summary of weights in it.
Yeah, yes, I think, yeah. I think I understand this.
Okay, Masoud, do you understand? So
it's fine, yes.
Okay.
So the root has to be in the path.
The root can be in the path, yeah.
But it's not mandatory.
Yeah. Okay. So next, try to talk about second task connected with the dynamical programming and tree. We have time. Yeah, 10 minutes. Okay. Do you know what is a independent set? Of vertices.
No.
It is set of vertices that are pairwise unadjacent. Or these are adjacent. I don't know. No, adjacent.
So it's a set of isolated vertices? Or not necessarily?
I can draw the example. Pairwise, no adjacent, it's equal to there are no edges between them. For example, these three vertices will be independent center vertices because due to absence of the edges between them.
Yes.
So task finds the maximum independent set in the tree. Interesting about this task that if we change tree for arbitrary graph, then this will be NP complete task. Do you understand? Yeah. So it's very complicated to solve problem in the arbitrary case. But in the tree, we can find maximal independent set by dynamic programming, or by dynamic algorithm. And do you know how to use dynamic programming to find independent set in the tree? As the previous task, you can remember how we find the passes here and try to repeat this algorithm for this task. How to find independent set in the tree? Firstly, it is main part of the dynamic programming. What we need to do? Yeah, we need to divide big task for some subtasks. And how we can divide it in the tree?
The maximum independent step in the tree is if you divide the tree, we will have the maximum independent step in the subtree.
Yeah, we divide it by finding the independent set in the subtrees. Yeah, but it's not so simple. There are some problems with this. Okay, we can say that this subtree 1, subtree 2. We can find independent set for one subset or for the second subset. Okay, and you want to say that the maximum subset of the tree is the union of these independent sets. Yeah? But it's not true, because if you try to understand what is return value of this algorithm, you understand that your algorithm return only these leaves of the tree. And of course we understand that we can add, for example, this tree, this node, yeah, etc. And how to improve this algorithm, not to get the false answer, to get the right answer in this case. We can say that there are two distinct cases of subtrees, of the independent sets in the subtrees. One case when we find independent set that doesn't contain roots, and the second case that contain root. one case. Doesn't contain a root. Second case. Oh, I use difference. Contains roots. For example, for this tree, I can find this independent set as the independent set that contains and this independent set is the first case. So we add two arrays. Yeah. For example, independent set contains root. I think that it is understandable. Independent set that contains root. Second case. Okay. Second case. Array. Yeah. And first case array. And so if we have root connects with two vertices U and V, or U and C, and of course I draw always two subtrees, and of course we can have different numbers of subtrees, of course. It can be not a binary tree. But in the common case, it is similar to this rule. So, firstly, if the is leaf, do you remember what is it?
Yes, it doesn't have children.
Yeah.
Yes.
So, first case, I write it shortly to spend my time. Our first case of V equal to 1. Second case of V equals 1, 2. And then if V is equal to root of the tree that have different subtrees, we say that firstly doesn't contain roots. In first case, roots of 3 or subtree. We say that first case of R equal to doesn't contain root. So we can get union of two independent sets in different subsets. Yeah, it is second case of U or second case of T. Is it understandable? And of course, if R has a lot of children, we need to summarize all of these children. And second case, if we find independent set that contains root, we say that roots plus, yeah, plus we cannot add children of the root to the independent set because they're adjacent to the root. So we need to add all the maximum independent set that doesn't contain children. So we first case was the O. First case was a T. And that's a recursive formula for the computing of the these two arrays. And then how to find answer for our question. What is the answer? Yeah, it is maximum. Of these two, F case and S case. And you see that oh,
R, I think.
yeah, R. Yeah, you're right. And you see that we repeat it for all the vertices, so time complexity is equal to O from number of vertices and space complexity too. So, as you see, the main is the summary of the lecture. Yeah, you need to use dynamic programming in the way when you divide task in the subtasks, and as in the last undivided concurrence. Oh, divide and concurrence. Because I talk about it, but it is these two topics connected are connected. Divide task in the subtasks firstly, and then find recursive or dynamic connection between the subtask. So about next time, we talk about other tasks that connect with the dynamic programming, And we talk about, we work here with the trees and with the arrays, but there are two-dimensional dynamics. For example, for matrices, or we talk about added distance. Do you know what is the added distance? Added distance between two words. We don't know, and we talk about it next time. And we find two-dimensional dynamics in it. And we talk about, I need to find two-dimensional, yeah, and other tasks, because there are several traditional tasks that you need to understand in the topic of dynamic programming. And in the end, I need to say that every time before you realize your algorithm, you need to understand what way is better to use your algorithm, in recursive way or in the dynamic way. We see now that in some tasks, when we divide it to subtasks, there is recursive equation between recursive equations appear, and in this way you can use recursive algorithms. But before it, we find different tasks that we can solve by dynamic algorithms and spend only linear time. So every time ask yourself what is the better way to solve the task, dynamic or recursive. And for today I think it's all.